In this active circuit that is designed using two ideal op-amps, we want to show that for the output voltage, if the waveform of the output voltage is like this, which at time 0 is 6 volt, and at some point after some amount of time it switched to negative 6 volt, as you can see after some transient. We want to say that and show that the time it takes to get to the final value of negative 6 is about 80 milliseconds. Okay, so to get that, let's focus on what's happening at the input. We have a 10 volt and a negative 10 volt on two sides of an RC circuit in series. Remember that nothing goes through the input of ideal op-amp that is properly biased. We make the assumption that these op-amps are applied plus minus 10 negative volt, 10 volt positive and 10 volt negative volt as supply voltages for both op-amps, as you can see. Now, at time 0 and before time 0, this switch is closed. So this switch is closed up to time 0. And because of that, there is no voltage across cap. A 10 volt shows up here. Across this resistor is 20 volt, and it causes some current that is going through the closed switch and then toward the resistor. All right. In that case, 10 volt is, 10 volt is here. And because of that, op-amp immediately at the output saturate to 10 volt. As you can see, 0.5 R is nothing compared to the series of 6 R. So 0.5 R is very small. Effectively, majority of 10 volt wants to show up here, like for example, say 9 volt. But we have two Zener diodes in series here, and they are 6 volt Zener diodes. So as soon as anything more than 6 applied, it will clamp the output to 6 volts. So all I'm trying to say is, at the beginning, the 10 volt is saturated voltage at the output of the op-amp number 1, and 6 volt is clamped voltage at the output of this circuit. And here we only have a simple buffer, so 6 volt appears at the output as well, as we see here. That's the situation up to this time 0. At time 0, this switch actually open. So at time 0, this switch open, and because of that, now cap voltage is still at time t, at time right after 0, cap voltage is 0, but there is now this current that is now passing through the series of R and C, and it starts charging up the cap. So we know that for a simple, this is a simple, let's say this situation here is a series RC circuit, and it's easy to write the equation for series RC circuit, but effectively it is well known that the voltage of capacitor is voltage of cap at infinite time, so at time equal to infinity, plus voltage of the cap at time 0 minus voltage of the cap at time infinity e to the negative t over RC. RC is the tau or time constant. Okay, so what is the benefit of this? Well, think about it this way. At time 0, voltage of the cap is 0 volt, because there is no voltage across the cap, because switch was closed and it didn't allow the cap to accumulate any voltage. At infinity, if you circuit, after you open the switch, if you let the circuit charge up the cap, at the end, the plus minus 10 volt will appear across the cap. Resistor will be nothing. So at infinity, you have 20 volt across the cap. 20 volt here as well. So all I'm trying to say is the voltage of the cap becomes effectively 20 volt, which is V cap infinity. And then knowing that 0 volt is V cap at time 0, you get to this simple equation, minus T over RC. And RC, given the values of R and C, which is 100 kilo ohm times 1 microfarad, give you 0.1 second. So it's 0.1 second. Okay, so let's use it here, 0.1. All right, this is the formula for voltage of capacitor at, starting from time t equal to 0 and onward. So I'm going to just write t let's say greater than 0 or greater than or equal 0. Okay, now what is happening here? Well, as the voltage of cap, so let me put it back, what the resistor we have. So here is the resistor, and here is the negative 10 volt at the bottom of the resistor at the input of the system. As the voltage of the cap is increasing, voltage at this node is dropping. So initially the voltage at this node is 10, but then it starts going down as the voltage across cap is increasing. So 10 becomes 9, becomes 8, 7, 6, 5, 4, up to plus 1. As soon as you hit plus 1, what is happening is, since 6 volt is at the output, and 6 volt is just doing a voltage division across 5R and 1R, what happens is you have the voltage division of 6 across these two guys. Effectively, at this node, what you have is 6 volt times R divided by R plus 5R, which is 1 volt. So plus 1 volt is here. As long as we have 6 volt clamped at the output by the Zener diode. So the voltage at this node start dropping up to the point it hits 1 volt. As soon as it hits 1 volt and goes below 1 volt, then suddenly the negative input terminal of op-amp has higher voltage than positive. Therefore, immediately it switches to output to saturation, negative saturation, so it is negative 10 volt, ideally equal to the negative supply. As soon as it's negative 10, since again 0.5 R is nothing compared to 5 R and R in series, output become negative 10, but then the other Zener diode kicks in and would clamp the output at negative 6. As soon as it's negative 6, then we have the same story. Negative 6 times R over R plus 5R will give you negative 1 volt. As soon as it's negative 1 here, then it becomes the situation that if the positive terminal is still plus 1, we go back to the previous situation, because now positive terminal has higher voltage, so it becomes plus 10. So the circuit basically gets into this region, in which it is a transient region. It starts oscillating. The point that we get to the final steady state change of a state, which means this amount of time, is when we really get to negative 1 volt at positive terminal. So as soon as we hit negative 1 volt, then we are done. Because below negative 1 volt, the circuit gets to the steady state of negative 6 at this node, and negative 10 at the output of the first op-amp. So long story short, we need to get to negative 1 volt between for the voltage of the node between cap and R. By R I mean 100 kilo ohm, and by cap I mean 1 microfarad, as is given in this circuit. So therefore, the story becomes, if I want to get to negative 1 volt, if I want to become negative 1 volt here, I'm going to show it here. So I would like to get to negative 1 volt for the voltage of the node between cap and resistor. That means the voltage drop across the cap is 11 volt. Because on one side is plus 10, on the other side is negative 1. So basically, my target is voltage of the cap should be 11 volt, and the equation says equal to 21 minus negative t over 0.1 second. Okay, so the only thing I need to do is I just shuffle things around. It becomes e to the negative t over 0.1 is equal to 1 minus 11 over 20, which is obviously 9 over 20, and then that result in final outcome, let me write it here. So that result in final outcome that we get basically t is natural logarithm, or ln, of 20 over 9. Okay, so if you compute that, let me just write it there. So if you compute 20, and I forgot a 0.1, I'm going to take care of it. 20 divided by 9, and then take the natural logarithm, is become 0.7985. So I forgot also a 0.1. So 0.1, and it is t equal to, so it become 0.1 times 0.7985, which in seconds, so effectively this is in seconds, so effectively it's the same as saying 79.85 millisecond, which is what we were chasing. So roughly it's 80 milliseconds. Okay, so I hope that this example is helpful in terms of being able to analyze the impact of a transient situation in the case of RC circuit combined with ideal op amps when we have a transition in the circuit.